Okay guys, let's take a look at today's lesson. What we're going to be doing is we're going to be looking at systems of polar equations. We have graphed polar equations, we have looked at complex numbers in polar form, we've switched polar equations from polar to rectangular and back and forth. Now we're going to move into systems. We're going to graph two graphs and determine where they cross. So normally, our point of intersection of two graphs is that's a solution, right? We saw when we were working with parametric equations, we saw that, remember the spider and the fly, where they didn't really, they looked like they crossed, like the curves crossed, but they really didn't get there at the same time. It's kind of the same thing with polar. Polar equations may look like, the two graphs may look like they cross, but if they don't get there at the same angle measure, we really don't consider them crossing or intersecting. So it just provides a little bit of a little nuance that we need to be aware of. To the first day, day one, we're going to use a calculator. So hopefully you have your calculator with you. If you would be sure you have that out. We're going to walk through one example. So I have it split down to 3 steps on how to solve with a calculator. And step 1, what we're going to do is we're going to graph the polar equations and sketch them, in our calculator. And we're going to sketch them on the graph. You are pretty good at graphing the polar equations. You don't necessarily have to use your calculator to graph them, but you certainly can. And then we just sketch them on the graph that you're either provided or that you would create. Step 2, we're going to plot the auxiliary Cartesian graphs on our calculator. So, the polar mode of our calculator is kind of nice. It can show us pictures of polar and stuff, but it really can't do intersections. And to be honest, the reason is they're so complex. Each location on the polar grid can be represented an infinite number of ways, so the calculator's like, yeah, no, I'm not even going to try. So we're going to go into Cartesian or function mode to graph them so that we can truly see where they intersect. Then we're going to go back to our graph and we're going to circle the intersection points on our graph just to try to tie it all together. Where are they actually intersecting? Because that's what we're going to be looking at. So let's go to our example on the next slide. So we're going to solve the following system using a calculator. So let's go through our steps. The first step is we're going to graph the polar graphs. So let's pull up my calculator, and if you would kind of follow along with me. So we're going to switch it into polar mode because we want to see what the actual polar graph looks like. Okay, so let's go into our mode, and right now we do need to be in radians, so be sure you're in radians. Then we need to go down here and get into polar mode. So let's scroll down and go over to polar mode and hit enter. Okay, so now we're in polar mode. So let's go to our y equals. This is where we're going to graph. Now let's type in the two graphs. So the first one is 3 plus 2 cosine. So 3 plus 2 cosine theta. Okay, that's our first graph. Our second graph is going to be 5 sine 2 theta. So 5 sine 2 theta. I'm going to go in and look at my window and see what's going on. So I have starting at 0 and going to 2 pi. That's probably going to be fine for these two equations. If you get a more complex polar equation, you might want to pay attention to how far to go. Our step, this is just the default step. You probably should just leave it alone. What that does is it decides how many points to plot. It tells your calculator how many points to plot. And this, we'll just stay with the standard window. Let's see what happens when we go with the -10, 10 window. So let's go ahead and graph. All right. So there are our graphs. So we can see the rows that, what was it? It was 5 sine 2 thetas here. And our other graph was the 3 plus 2 cosine is in the blue. So what we're going to do is we're just going to take these figures and we're going to sketch them on our paper. Okay, so let's go back to our paper and let's just sketch them. Okay. So I'm going to sketch the 3 plus 2 cosine first. So I went ahead, I actually did graph them. You can look in, it can be a sketch. It needs to be fairly accurate because we're going to be using these angle measures to determine where we're actually intersecting. So let's just do that. I mean, that was 3. So something like this. Okay, so there's our 3 plus 2 cosine. So let's go ahead and graph our 5 sine 2 theta. That one came out, the petals are 5 rings long. So we're just graphing all of those so we can get an idea on what's going on. Now, just a preliminary check. I mean, it looks like, if you look at this, 1, 2, 3, 4, 5, 6, 7, it looks like there are 8 intersections. But we're not sure, so that's why we have, so this is our step 1. We just sketched our graph here. Step 2 is to, let's find out what's really going on. So our step 2 is where we're going to go back into the calculator, and this time we're going to go into function mode and see exactly where these guys intersect. So let's go back to our calculator and let's go into function mode. Okay. Move this out of the way. Okay. So go to mode, and we're going to go to function mode. Okay. Okay, so we're going to function mode, and then let's go to y equals, and we're going to type in those two equations again. So 3 plus 2 cosine, 3 plus 2 cosine, and this time it's an x because that's just what the calculator does for us. It switches it. And then in y2 we have 5 sine 2x. Okay, so now let's graph them. Let me look at my window and see what we have going on. I really don't need the negative x's, so I'm just going to start it at 0. I'm really interested in 0 to 2 pi, to be honest. So I'm just going to start at 0. I don't really want to deal with the negative x's, which in our case are going to be negative thetas. So I'm just going to graph it like that. So let's see what we got going on. Okay, we have lots of intersections. Let's go ahead and start calculating them. So we want to look at this intersection first. So we would do our second calc. Our intersection is number 5. And then we would, just going to scroll over there. I'm going to start with my smallest angle measure. Okay, and let's see what that is. Okay, so now this is going to be interesting for us because it's really, let's think about this for a second. X stands for the angle measure, right? X is the angle measure, theta. And we write our points r theta. That's how we write our points, right? It's r theta. So I'm going to start a list of points up here. So this is actually theta. It's not r. This is r. So our point is going to be 4.653 and then 0.598. Okay. Alright, so let's look for our next point. And this angle measure is the smallest one. Okay, so let's keep looking. So second, calc, we do our intersection, and let's kind of go to this next intersection and take a look at that one. Okay, so let's write that one down. Let's see, I'm just going to go up. So we have 3.851 and then 1.131. Okay. All right. Let's look at our next one. So second, calc, intersect. Let's go over here and take a look at that one. Okay, there's that intersection. Let's copy that one down. Let's put it right here. So that ring measures 1.010 and then 3.243. Okay, and let's look at this one. Second, calc, intersect. Let's scroll over to that one. And copy that intersection down. So that is 2.486 and then 4.452. Let's think about this for a second. 4.452. Okay, let's keep going. Remember 2 pi, what is that, around 6 something? So we really probably don't want to go past that. So let's see what this next intersection is. So second, trace, intersect. So let's go over here and see what's going on over here. Wow, that angle measure is 6.88. Okay, so that is more than 2 pi. So it looks like it's starting to duplicate. In fact, let's look at the ring measure. Look at this. It's 4.652, 4.65, well, 4.653, 4.653. So this is just a complete rotation back to this same, excuse me, intersections, back to the same intersection. So it looked like we had 8 intersections, but in reality we only have 4. All right, let's go back to the graph and go with our step 3. Okay, so there was our step 1. Our step 2 was to write down all those graphs, or excuse me, the intersections. So let me just recopy those. So step 2, we had okay, so that's what we had going on. All right, so the last step, step 3, so step 3 is to circle our solutions. Let's see which ones of all these 8, let's see which ones are actually solutions. So this, remember, is R, and this is theta. So we'll just go to theta first. So that's why we have these numbers here, to just kind of help you judge what those numerical values are. If we go to 0.59, about point to be somewhere over here. So we're looking at like probably this intersection right here. Let's see, 1, 2, 3, 4. My rings are 4 out. My drawing isn't perfect, as we all know. That seems to be about right. Let's do our next one. So the angle measure is 1.131. So that should be in here somewhere. Looks like I should have had this a little wider, but that looks like it's referring to this one because the rings are at, well, yeah, my graph is a little bit off, but that's okay. It's all right. It's okay that my graph is off. We're just sketching. So we've taken care of these two intersections. So let's look for this one. So our angle measure is 3.248. So here's a 3.1, 3.7. So it should be somewhere in here. Our rings are around 1. So it looks like that's that intersection. So we got that one. And then angle measure 4.4 puts us where? Puts us over in here somewhere. And looks like this is that intersection. So those are the actual intersections. These, though they look like they cross at different angle measures, so they really don't meet at the same angle measure. They meet at different angle measures, kind of like I was explaining with our parametrics. So we really just have those 4 solutions, and those would be our answer. Okay. Those would be the answer. Okay.